All right, we're live for day 24 of Admin the Code. Mm. 40 minutes for a bit of refactor and warm up. So yesterday, I wrote this code for part two. Um, this is a brute force search, and I gave up. I walked away, and when I came back in the morning, this happened. I had the answer down here, and it only takes a minute to run it. So if I had just run this code, I could have gotten this like at least 10 hours earlier. But it's still not completely satisfying that this is you know, a minute long brute search. So I think I'm gonna fiddle with it a bit. One thing I might do is to keep track of my visited, I might use a bit set instead of indices into the nodes. So I might reference nodes only by their index. Right, the position doesn't matter anymore. So let's do that. Um, what is this? This is my adjacency graph. Oh, and this is what I use to print out my graph viz. I can pull that up real quick. Um, where is? I think it's just my whiteboard. Yeah, this stuff here. This is a great tool. You can output the input to this programmatically pretty easily. I'm very happy with it. But what I want to do is really turn this into a map from indices. So let's see, we have all our nodes. We do still need, okay, to call adjacent nodes, which does a search, we still need to use positions. But after that we can have indices. A node to the list of adjacent nodes to that node. Um, hmm. I could just give them indices separately, or I have to give them indices separately first. Val indices equals nodes. Is this a set? Nodes.to list. Let's order by distance to the end. Order by dist to end. And then I'm gonna zip with index and to map. Okay. Oh, it's sort by. Okay, now when I'm making this map, I can have this go from int to, what's this point in int? Oh, that second int is the distance. I wonder if I should maybe give this a type, my node ID, but we'll do this. Indices n. Let's call this index of n, and then we'll take adjacent nodes, and this returns a list of states. No, adjacent nodes returns a list of points, right? Points and distance. Hey, yeah, yeah. Hmm. How was it? Sorry I couldn't make it. And where were y'all? Let's do this. This is I'm gonna unzip this. Well, hold on. I'm gonna map this. Index of the node. And then this right side can just be the distance. And this tuple or this list, uh, um, that works. That works. I'm just gonna change this so it's just printing the index on P and Q. Oh, yes, right, right. Are you still there? I'll call sometime soon. Okay. And what is this doing here? Sort by dot x and dot y. You don't need to do any sorting. Oh, yeah. We don't need to do any sorting. So P and the D's, PDs. We still need to take PDs and map. You know what? This is just for drawing the graph. We don't need that right now. I just want to see how well this works. And for now, I'm going to comment out the final run here because I have errors to fix and I don't want to run immediately after. Here, edge node. So node is not an index. And edge, what does it take? It just takes the int. And visit is going to take a bit set. We need to import that. Okay. Now, what's going on here? My state, search state, has nodes. Path. Path is a list of search state. I think what I could do at this point, the bit sets might be small enough. I can just make them part of my search state. This should still work in theory. Set int. Um, I guess we could turn that into a bit set. S.node equals index of int node. bit sets, apply. Okay, that's back to working. We can get that a run. Oh, index of start. Empty, not max. Interesting. Um, so what happened here? That makes sense. Index of. Oh, hold on, hold on. Um, just look at 2. And I assume 1. Oh, it's all connected to itself. Let's fix that real quick. So n, we have index of n. Shouldn't be index of n, it should be index of this point. And I think I want to sort it differently. Where's my sort by? I think I want to sort by distance to start. But it is running in the meantime. There. That cut down 40% of the time. How fast did that run? 20 seconds. Cool, cool, cool. I think we could do better. But let's get my graph code working again. So PEPDs, these are lists of int and int. PDs.map, this can just straight up be, wait, P, it's not point anymore, but we have P, D, and then P2. And I do want to see what this graph looks like. Let's copy that worksheet output and visualize it. Look at that. Um, Syntax error in line 1. Near the quotes. Can those not be names? What was it previously? Oh, you have to keep the graph. Oh, we didn't dedupe. Okay, we do still need to dedupe. But I mean that looks all right. Um, I guess that's why we normalize here. Yeah, let's do this. We can do, or you know, we're just gonna do min and max. P dot min p2 and p dot max p2. Okay. And I think I can make this even faster in exchange for some memory, or this path at least. This path could already be a bit set, right? Hmm. Yeah, we don't necessarily need to put it in a search state because we're doing a DFS. And we can start with a bit set.empty. Let me just add that path in here. Now to add to the path, we do, wait, state, this is state. All we care is the position. Path plus state dot pause or search state dot node. We can try that out. In the meantime, let's look at our new graph is. Oh, hold on, we don't have this yet. Okay. Oh, we forgot to uncomment it. Okay. Let's try that out. There we go. That is much cleaner. Just screenshot that and add it to my whiteboard. Oh, nope, nope, that's the whole thing. There we go. And how are we on performance now? We're down to 5 seconds. Fantastic. Okay, so I was debating someone about this, and I'll respond to them. So I think the reason that this bit set works and drops it from however many to 5 seconds, like over a minute to 5 seconds. So each state makes a few checks. So I don't think the size of a visited set matters here. What matters more is a sheer number of states, and that each state makes a few checks against its visited set. Um, Much better. Well, let's see. So that's many hash computations for all of those things that's checking for all of those points. Um, but checking in a bit set becomes like a single operation, right? Is a single operation against a bit masked number of some sort. Doing this dropped my time from over a minute to 5 seconds. Okay, and I'm gonna spoiler part of that. There it is, there it is. I am happy. Great. So we have performance optimization. Now let's just clean it up. And let's generalize it for both parts. I'm gonna add that in. Performance optimize 2023 day 23 part 2 bit set. And let's do some cleanup. Oh, hold on. My stream health seems to be suffering. Let me just check on things real quick. Hmm. I am dropping 58% of my frames. Give me a sec. Fixing these issues. Hmm. I'm just gonna run a quick speed test maybe on another device. So be right back doing a speed test against on my phone. Mention that in my Discord too. So I'm gonna just reply to myself here. Instead of a set of points. Yeah, using a bit set instead of a set points. Visited. Dropped my time to 5 seconds. Mhm. So we have our graph is. Let's generalize this for part one. Let's do some cleanup. Um, Next path. I mean, this is good. What we could do, I wonder if I made this tail recursive. Let's call it all paths 2. Comment this out. So all paths 2. And let's have our states just be a list of search state that we're still going to handle. And we could still make this a DFS. But the end result here, instead of a list of search state, actually, you know what? I want to see how many search states we end up checking. So let's do this. Note size. Give it 5 seconds. There are 1 million states. Yeah, I don't think I want to make that breadth first search because we'll have too many states at a time. So we will keep it depth first. And, oh, you know what? Hold on. I'm checking my stream health. So, uh, hey, VP Monk, how are you? How are you? How is my stream health? It seems like I'm dropping frames, so I'm just checking on my internet here. Welcome to the stream. Are you doing Advent of Code? Let me see here. Yeah, we're still in the red. I want to make sure that we fix this before the problem actually drops. Um, I guess the only thing we might change. Well, okay, can I make DFS tail cursive? Um, yeah, my upload is a bit low. All I can do is hope that my internet gets a little bit better tonight. Right now, actually, it seems healthy. Let me see. Yeah, it's better. Okay. Um, anyway, yeah, just doing some cleanup. States. I think we could just add this on the head of the states. Add all the next onto the states to search. Oh, well, that's going to grow pretty large then. We're going to have a list of 1 million states. I don't think we want that. Whereas if I do this way, I might have a stack depth of at most 36. Yeah, the way I have it right now, stack depth at most 36, and at each stack there's just a bit set, which is going to be of a vector of 1 long. So 1 long, and then search state has 2 ints. And at most 40 of those on the stack. I think, honestly, I have it the best way already. Okay. Let's get rid of some junk. Yep, but the graph is at the bottom. So we have node indices. We don't need this SS. Adjacent nodes. This, where do I use this? creating our JSON graph. Can I make this cleaner? So what we do, we flat map next on these states, right? And these are, these are the normal states. Yeah, these are our normal search states. Move my normal state up above. Um, I guess this is walking state, and this might be like node state. So start point, end point. This here is where I might choose. I'm gonna make this a Boolean flag so I can generalize to part one. One-way slopes. So if so JSON depends on that. Well, JSON equals if one-way slopes. Then we had the part one answer. And that's not the part one answer. Let me pull that up. Day 23, 2023. It's this right here. And what is the value of this? This is an array of point. I guess I get to list this. List dot from whatever this is. And then now we can just say, oops, adjacent dot filter path. I wonder if I should make that a set actually. Then I could intersect path and diff visited. And we are returning a set eventually anyway, right? And we're returning a list of states. And how do we use it? We partition it. Honestly, it's so small, it doesn't matter if it's a state or if it's a set or a list. So that works, that works. So I'm just gonna start calling this one way or slopes. Yeah, slopes enabled. Oh, no, no, no. Hey there, Blue. How are you? How are you? Yes, yes, it is Christmas Eve. So um, I think you saw that my brute force solution actually worked. The last thing I wrote before ending the stream last night, it worked. I didn't see it work before ending the stream. And it only took a minute to run. And then I went through. That Simp was right about using bit masking. So I turned my set into a bit set, and it's a bit set over the indices of the nodes instead of a set of just the nodes themselves. So I don't have to do hash calculations, the million hash calculations that would come into play. And it went from a minute down to 5 seconds. Yes, Merry almost Christmas Eve. I'm gonna want to get this into a working state very soon. Why don't we default this? No, we'll just pass this. One-way slopes or slopes. I'll just say slopes on. Uh, yeah, I just want shorter names. Slopes on. And then I guess in adjacent nodes, you have to have a slopes on parameter. And we pass it on to this next. We have some really long lines that I'm not liking. So let's split this up. Now next. And then we'll just do next dot partition and completed. I think the next stage we'll just call it incomplete. Or we'll say to search. Whoops. So it'll rename the symbol to search. Hmm. And this, where is my edge used? I guess this has to be a def edge. Search state. You know what, we'll just make both. Edge part one. You know what? We're gonna table some of these changes for now. How do I do this? Max window. Okay, kill that. And we have, don't care about these untracked files. Look at my messy repo. And these changes, we'll just stage that and then stash the index. Day 23, 2023, day 23, cleanup. Okay, let's get that out of the way. And let's get ready for day 24. Okay. Twenty seconds to go. I hope you can finish too. For me, I'm not doing any of that stuff until tomorrow evening. No need to travel much. So I just get to sleep tonight. I have bread in the fridge and I'm gonna bake it in the morning. Okay, so we have triple coordinates. Are these large cubes? So hailstones. No making process, we're actually making hail. Hailstones are flying through the air in perfect linear trajectories. Position and velocity. Okay, left is position, right is velocity. And this is a 3D point. Great. I wish I had this ready. We're just gonna make new case classes and then define methods as we need. So day 24. And we call this input and val. I guess we have hailstones, which is going to be a list of two things. Point 3D, case class point 3D. Okay, you know what to do. XYZ. Oh, it even gives me a point. Cool. Case class velocity. XYZ. Let's rename that to velocity. There we go. Okay, so this is a list of point 3D and velocity. Uh, in fact, we're just going to rename this a point or position. Whoops. Typing 3D is kind of a pain. Hmm. Okay, input map. Not quite what I'm looking for. Um, so there is an XYZ, X comma Y comma Z, and an at X XV, YV, and then ZV. And those are all variables. Okay, Copilot can autocomplete that. There we go. So we have our input parts. How likely are the hailstones collide with each other and smash into tiny crystals? Consider only the X and Y axes. Ignore the Z axis. Looking forward in time. How many of the hailstones pass will intersect within the test area? Okay. So X, Y, we can ignore Z for now. Um, let's do this. Def XY equals point X and Y. And then we can work with areas. Or we'll just call it like lateral. Look for intersections that happen within X and Y position. Each at least 7 and at most 27. So that's the test area. Okay. Hailstones will cross paths inside the test area. Oh, interesting. So X now is integral. So just if their paths cross, we draw their whole line and do those points cross each other. So we can look at their start in the area, their end in the area. Let's see, let's do a def lat as well. Equals point xy for the velocity. Well, test area equals area 7 to 27. Two hailstones future paths cross inside the boundaries of the test area. We need to search a much larger area. Oh, okay. Look for intersections that happen with X and Y positions at least whatever that is. Jeez. Okay. Disregards the axis entirely. Those are those are large numbers. And my area still only works on integers, so we're gonna have to improvise stuff. Yeah. So we have a start position, which might be any of a bunch of numbers. And then we have a velocity. So we're not even checking if they cross at the same time. We're just checking if they cross over each other. Let's draw things. Okay. We're drawing in blue today. Or you know, we change that to white. I like white. So we have a big old area. There are points. They go somewhere. And we want to know how many of the points, which how many are there? Hailstones, that size. Wait, this should work. It looks like worksheets are not cooperating for the moment. This is why I should start and set that up early. Oh well. How many lines are there here? Let's just look at. How many cases? 300 matches. So we could do a 300 by 300 check against any two. And how do we know if they intersect? Well, this goes in that direction. We could draw a line to the boundary and then check if at any point. So what would work? There is this whole range that would not work. Anything between those two. So I guess we could look at the angle. We could do like cosine stuff. So the angle to the endpoint, the angle to the endpoint, and see if we fit within that angle. I just think SOHCAHTOA. So we have an X direction and we have a Y direction. And what we want is this. So we don't have the hypotenuse. Oh, hold on. I guess we want this with this triangle here. And we want these two angles and this other angle. Now, is there another way to do this? Let me. I mean, we can check. We can look at this distance, and we can move that distance and see if we are above the Y point here. But it's not going to be very precise, is it? Because yeah, so we can move that distance and then check. Is Y above that? And is X to the left of that? Either one being true would work, right? No. It depends. So these are also like systems of equations. So how do we check if 2 points intersect? Oh yeah, let's do an equation for each point. So let's say this is F and this is G. F is gonna be we have an X and a Y there. So whatever X coordinate times X plus Y. We could solve these for each other. Like at what point do they intersect? Is there a solution? Do we want to solve these like programmatically? Or yeah, we get their solution where they intersect. They will always intersect somewhere. And then we say, is that intersection point within this? But these aren't going to be full lines, are they? Right? If we just did that, then they have no intersection at all. So there might not be a solution. Okay, how do we turn one of these into the velocity? So it's x plus Oh, I'm just gonna check. I'm gonna check angles. So let's do angle. And given that we have x and y, so I guess tangent. Tangent is opposite over hypotenuse. Or wait, sine of this angle. Um, tangent of this angle, we'll call theta. And theta is opposite over adjacent. Yeah. So we get the inverse tangent of opposite over adjacent. If angle equals a tan, great. And let me check the parameters here. Coordinate. I'm gonna trust it there. And this is fine with. It's supposed to work on doubles. That converts to double. And then we want these two angles as well. And then is this angle inside those two angles? So let's do hailstones dot map. We have position and velocity. What we want is just the lateral position, p dot lat to v dot lat. And then yes, val lat hail. Let's call it lat hail. And then lat hail dot combinations 2 dot count. That's not exactly what we want, but we do want like A's angle. Let's break this down even more. So A at, we have 2 points. So we have A pause. Well, yeah, A pause. Does a velocity matter? Yeah, because that will tell us where the other intersection is. Oh. Mm-mm. We have to check its intersection with the outer area, which will always be there. And I think we can be dumb about that. So these are our boundaries: val min bound, val max bound. And then for B, we're fine with angle. Tail or lat tail. What do I define lat tail? Oh, hold on. It doesn't seem to be defined quite yet. Okay, this is not position and velocity because the hailstones. Wait, the hailstones are a list of positions. Oh, yeah, this should be a list of position, comma velocity. There we go. Now my autocomplete will be smarter. P V, and we just want P dot lat and V dot lat exactly. And now these are just 2 points. So A pause, A val. B because the velocity. Let's just call this AP, AV, BP, BV. And then we are checking. Let's just look at like BV.angle. And then we want A's intersection with the outside bound intersect A. Okay, min bound. Well, it's not exactly just that because this is in vertical and horizontal directions. So we have multiple to try for here. It's gonna have zero intersection with this. So let's say we have 2000 to 4000. This is for the 4000 top. So we'll say this is 4000 and we want to solve for y equals 4000. So let's say the velocity of something. Look. Let's get some velocity for here. Let's say v equals 3 across and 4 up. And position as a function of velocity. P. Well, we have px or we want to solve for y. I'm failing math. 3 times, I guess there's a time in here. So time times velocity. So px plus p times vx. And then similarly for y. And what are we solving for? In this case, we're solving for, so we have py plus t times vy. And actually t can be in terms of x. So it's py plus t plus x. The x value is going to be so this is the y value. We're solving for y equals 4000. Okay. Or, greater than or equal 4000. So, well, position y, actually position py equals 4000. Wait. This is a constant factor that we're adding. So if we were just at 0, 0, we would this. Okay, let's just do like x, y, right? This line here is y is equal to x if we're going along the diagonal. Um, um, and that is when velocity is something like 3, 3, I suppose. Um, I not linear equations. And when velocity equals 3, 6, then this is going to be like x, y equals 2x. So y equals that ratio, I guess. The y coordinate equals vy over vx. And it's not exactly just that, because you're gonna do the offset. So if this is like y equals x plus 10, then we have a graph like this, up, 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 up. And how does that translate here? Let's say they start at x equals 0, y equals 10. Then setting x to 0, this factor here is going to be plus y minus x, right? Y minus x equals 10. So plus vy minus vx. And whether we check for 4,000 or whatever depends on whether the velocity is positive or negative, right? So y-intercept. And we can do that. Um, and I'll give us the intersect, actually, whether it's going completely outside the box or not. So we still need to check if it actually intersects here first. Or, we get the y-intersect, we get the x-intersect, and we keep the values that are less than 4,000, that are within the range. Okay. Bound intersect A is going to be, I guess, two doubles. No, wait, not. Yeah, sure. Okay, so looking back at our graph here, or our math. So if y points north, well, y-intersect equals, so if av dot y is greater than 0, this is an option because it could be 0. And then the x value doesn't matter so much. So we're going to do like a max bound. So we solve for 4,000. Um, wait a sec. Um, what? So we have an equation for y. Let's say we have like x plus 10. And I guess we solved for the x value of that intersect. So when y equals 4,000, then which part here are we solving for? Which is the x value? I guess it would be this one over here. So 4,000 max bound minus Vy and Vx. We need you know what? I think I'm overcomplicating this. So let's see here. If it's 4,000, you can see how much it's traveled just by dividing by av.y. So val t equals max bound minus ap.y divided by av.y. Yeah. And then the x value would be exactly this, ap.x. um, plus av.x, the velocity, times the time. Okay. Else if av.y is less than 0, let me do something like that. And otherwise, we could put all of these, we can put all these in options. We'll just do like a sum. Sum around whatever the x is here. Okay. Oh, mathing. And then something similar for x-intersect. If it's a case, so if it's a case that the y-intersect, I'm calling it y-intersect, it's actually an x value. So x-intersect, or we'll call it top-bottom intersect. Yeah, top-bot intersect. Let's just say TB, and then we have our LR intersect. Okay, if TB intersect, I'm just gonna do a long if chain here. Dot empty, then dy intersect. Oh wait, it would default to. It would default to just y, right? So let's remove the sums. So we just have ap.y. And here we just have ap.x. Yeah. Okay, now we just need to look at those two values. So there's a left-right intersect, and that'll be a y value. So if it's within this range, then we keep that. So we do something down here. If our top bot intersect of the range, let's make a range here. Val bounds. I don't know why you would do that. Okay, min bound to max bound. So this is a inclusive numeric range. So if bounds dot contains should work on anything, right? Okay. If min bound is less than or equal to LR intersect and max bound is less than or and LR intersect less than or equal to max bound, then what we have is our LR intersect. We keep LR intersect as our y, and we have 4,000 if it's going north. Okay, so if AV dot y is greater than 0, LR intersect is our x range. It's always our x range. Hmm. Oh. And like in the case of the horizontal line, our LR intersect, our TB intersect will be AP dot Y. We're looking at LR intersect first, so this is a Y value. Yeah. Switch these two around. So we have for the X. This is the case where it defaulted. So we have min bound for the X otherwise. Or min bound for the Y. Wait, hold on. For the X, this is LR intersect, so this is a Y value. This shouldn't be AV dot Y. For the LR intersect, it should be AV dot X. So if it's facing to the right, then X value is a max bound. Yeah. And bound intersects can be double. So these are all going to be like two double. What is LR intersect? Why is this a long or an int? I guess we could do a two long here. And of course, it's expecting a double. And what if AV.x is 0? AV.x is 0. AV.x is less than 0 than that. Just handle that. velocity, then it just becomes x. And this will kind of be handled in both cases. Um, and then the y value. Well, if it's pointing sideways, the y value, wait, it shouldn't be. I think my intersect function is correct. I get different points than in the example. Yeah, I feel you there. This is gonna be hairy. I should have this kind of stuff in library code. So ap.x, not okay. So this is our left-right intersect. Our left-right intersect is going to be ap.y in this case. But ap.y up here it's going to be ap.x too long. So it's always going to be L or intersect. All that's going to change is like the y value. So if ab.x is greater than 0, it's going to be max bound for the x and LR intersect. Otherwise, it's going to be x for the x. ap.x. And then LR intersect will be given. Oh. No, hold on. LR intersect. It is a y value. It's going to be ap.y, no matter what. Right? AV, if the velocity of x is 0, then we're moving just up and down. And the left-right intersect, there's gonna be no left-right intersect actually. Yeah, there's no left-right intersect. Yeah, oh whoops. Okay. This is a none. I was confusing myself. Okay. Let's fix that real quick. None. I wrote none initially. I don't know why I confused myself. Yeah, I bet you would. Yeah, I should be. I can't think linear algebra right now. Not on the spot. I'm having to. Right, like I should just be able to like solve a system of equations. I'm just doing this by hand because I can't think of like how this maps to matrices. And I wish I had that under my belt, but that's a thing to handle. Okay, so let's do this. If LR intersect is empty, then we get top bot intersect. So there's no left right intersect. Yeah, left right intersect is a y value. And if so the x value would be top bot intersect. We should be able to get it. They can't both be empty. And this will depend on which way y is going. So if av dot y is greater than 0, then max bound, else min bound. They can't both be 0. Right? 0, 0. Good. Dates handle that edge case. Yeah, using Unity, definitely. Okay, else if TB intersect is empty, then we should have something analogous to what I have up there. AB.x greater than 0 and the max bound else mountain bound. So the x direction, I guess my y direction points up now. So AB.x is, well, yeah, that's fine. Not using like north, south, east, west. Otherwise, we get them both out, and then we go into here. And then they're both greater than or equal to 0 or whatever. So min bound at the intersection of the square is annoying. What I should have done to intersecting with the square is just look at the intersection between the 2 points. That would have been so much easier. And that's what I'll do when I refactor, I guess, because I'm almost there. So if min bound, if LR intersect y value is contained within min bound, wait, where is that? Okay, if this y value is contained within here and not up here, then we know the y value. And if right, then we use LR intersect as our y value, and as our x value, we use depending on the direction of x. So if AV.x is greater than 0, then max bound and LR intersect, and then we're just going to do an else here. It's not going to be 0 at this point. And then else if, and this doesn't even need to be an else if, it's just going to be the else. If AV.y is greater than 0, well, here, I guess that's a dot get here. Dot get. So if we point north, that's 4,000, else 2,000. Yeesh. Okay, that was a pain. But now we have the bound intersect, and now we can do some math on those angles. We have to sort of go clockwise. I didn't think about going clockwise. I should have looked at the intersection between these 2 points. I really should have. But they're not full lines. So I wasn't sure how to handle that. Hmm. Um, A angle 1. Or angle to A. Yeah. I guess angle to. So what do we have? We have a point here. We don't have these two dense distances. We have we could get this angle from here to here. Let's take a look at this. Man, throwing in Z is gonna kill me. Okay, so we have an angle south. Or let's just draw something somewhere else. So we have our A point or our B points. If we have, let's say we put A here, and then we have some intersection somewhere. Um, and what we want to know, so what we do have is the angle of this thing, right? Starting from here. So, let's say that's going there. We have this angle. We also want this angle. And SOHCAHTOA, we have opposites. We have hypotenuse. Oh, we have all of these. Okay, we can just arctan this again. Yeah, and then we check the angles between those two. Um, but wait, in which order we check if it's between those two? I guess we just take like min and max. I mean, what if the angles are like, well, hold on. These two are going to be closer along some angle, right? Like how far away could it go? Let's say we have here, we have these 2 points. Let's say the intersection is all the way over here with this one. And we want to check that angle to that angle. But how do we choose which one to put first? I don't know. Let's just get those angles first. Angle to A. That can't be right. BV dot angle minus AB dot angle? No. Reading got you again. Oh, what did you miss? So we have math.a10. And the y would be bb.y minus ab.y. Yes. Now angle to intersect or bound. Let's say that. Angle to bound. Okay, math that. Nope. A10 2. And you know how to do this. Cool. Y's and x's. And how do we determine which one of these to do first? I guess it might depend on AB dot angle. Okay. Let's say this point here is B. This point is A. You must ignore z-axis. Yes. Yes. I'm glad I didn't. Oh, awesome. Awesome. Great. Okay. So in this case, if it matches the angle from, oh, okay. So if it matches the angle, then there's nothing. Or if it matches the angle, then, we would do, check that's between those two, whatever. I'm so afraid of like floating point rounding errors here. But I hope the input's just designed not to fuck with us that way. Okay, and if the angle if the angle is greater than or less than this angle. So if a theta is less than b theta, or b to a theta, yeah, less than b to a theta, then we check if I guess we have the intersect theta. So here's the intersect theta. Check if b theta is greater than intersect theta. No. Yeah, greater than b theta. So if b theta, basically if b theta is greater than a theta, then b theta should be, oh no. In this case, b theta here will be to a theta, right? B to a theta is less than a theta. Does b theta even matter there though? You still have to check that it's between. Let me check that b theta is greater than I theta, and b to a theta, or no. B theta is greater than, what are these angles I had? Angle to A. So we have our we have our b to a theta. This one here. I need to be between these two. So check if b theta and b theta is less than b to a theta. I'm worried about. Now I'm worried about like if we are right on the 0-360 boundary. God damn it. Okay. Participants? How are the participants here? That's kind of weird. Where are the participants? Oh, I hate Microsoft Whiteboard. I'm switching off of this next year. Or after Advent Code, I'm gonna find other stuff. But we already checked B2. This is if B2 A theta is greater than A theta. Or wait, A theta? Oh yes, we're checking against A theta, the angle that this goes. Right. It's if A theta is less than B2 A theta, then we check this range. Otherwise, we check the opposite range. Okay. But what are those angles that we could have? So let's look at edge cases. Let's say A theta was like down here. Basically, if it's in this range, Let's look at some values for A10. It's going to be 360, isn't it? Math at A10, 2, and let's say x and y are 1 and 1. Well, y and x are 1 and 1, right? And if y is 0, this is going to give us 0. Y is -1. Well, we get negative values. Are these radians? Let's say y is 0, and this is -1, 3.14. Yeah. L intersect. I guess we do not get. Okay. So we have our three angles. Um, how do we check if it's between two angles? We could look at our A angle. We could add 2 pi to it, or we could add pi to it. Subtract pi from it. So we look at our A angle. And subtract pi from it for our min bound. And we check if I I don't know. I don't know. Um, this is our A. This is our B. Less than. I guess yeah. A theta minus pi. So if B theta then is in this range, but B theta here might have a very high value. I guess we could do it like bipartite. So what we actually mean here is this B2A theta is either greater than A theta and less than I guess this depends on if A is greater than pi or not. Oh my god, I hate this. I hate this. So if AB dot angle is greater than pi, let's say if it's less than pi, or yeah, if it's greater than math.pi, I don't even know if it's like greater than or equal to. Yeah, it's greater than or equal to, because we have 0. Great, so now we're going to return 360. If AB.angle is greater than math.pi and B to A theta, and angle to A is greater than a theta. Does that be greater than or equal to? I guess greater than or equal to works. And now, if it's not greater than I, now we have to check that either it's greater than a, could be a theta. Yeah, could be 0. Oh, and then we have to look at the other angle of it. So this is the case here. So what we're checking that beta A is greater than this A angle. It could be the case. Oh, this depends. This depends not on if A. Well, hold on. Yeah, we just check if it's within. No. So there's a beta A angle, right? And what we're checking, um, yeah, this angle does have to be greater. There are like multiple ways this can go. So we're checking basically if it's less than this value here. We're checking if what is less than that value. I hate this. This should be easy. If I knew how to do this, it would be done, is what I'm saying. So all I want to check right now, we're given B, we're given an A. And then right now, I want to check either this range to the right or this range to the left, depending on where A is. So if A is greater, like in this case, greater than this angle, well, first we want to check the case of this one here. We want to check if it's in this range. And to check if it's in this range, if that angle is less than this point here, if A is less than that beta A angle, or no, if A is less than 180, okay, so A is less than 1. If beta A is less than 180, right, then we have to worry about this overlooping. So what we've written here, angle to A, if angle to A is greater than 180, we don't have to worry about it. In this case, angle to A is less than 180. Then we check that either B is greater than whatever the angle to intersect is, or we check that we check that the angle to intersect is less than, we have these two ranges. Yeah, the angle to intersect, we want to be to the right of it. We want to be to the left of the angle to intersect. So we're checking that the angle to A is greater than AB dot angle. I guess it's always going to be greater than AB dot angle. Even in this case, it's going to be greater than, well, if the angle to the intersect is here, then we just have to check greater than, right? If the angle to intersect is greater than 0. And otherwise, if the angle to intersect is not greater than 0, then we do a different check altogether. So we're not going to try and put these each together. Man, there's got to be an easier way. There has to be an easier way to do this. There is an easier way to do this. Oh, the Copinger. Thank you for the raid. Party of 18. Welcome, welcome. So we're doing advent of code here. We're doing some math, and my fear here is that I've done harder math than I need to do. Because we have a hailstorm. We're looking for points. They have their velocity, their xy velocity. We're not thinking about z right now, and we want to check if they intersect. And my method so far has been, to find it. Oh, whoops. My method so far has been to find the intersect of one point with the bounding box that we're checking. And then I thought, oh, okay, once we get that, then we just have to check if our angle is between these two angles. But which two angles, like, right? The problem now is that these two angles, we don't know like which one needs to be greater and which one needs to be less than necessarily. I just think I can find that actually in an easier way than I've been trying to find it. And we also need to handle the case where those two angles cross the 360 point, right? And then we need to check both of those. Right, a smaller function is an angle between two angles. So def between, let's say angle between. So we have an A1, well, we have an angle that we're checking. Angle, which is going to be a double, min, double, and a max double. And min and max. Um, if min to, well, now it's ambiguous, right? Min, I guess we're gonna say clockwise or counterclockwise. So we're gonna start min here. And we're gonna check if our angle is greater than min, or if the other one, hmm, I guess if max is gonna be less than, yeah, we're crossing over if max is less than that. And in that case, we just add 2 pi to everything. So let's do this. If min is less than max, then it's straightforward. Otherwise, if min is potentially greater than max, then I don't think this is right. You have to say, oh, I guess this is right. In this case, our min is here. Our min needs to be less than angle, or our max needs to be greater than angle, and either of those being true will work. We don't have to add 2 pi to anything. And then now we just need to find which one is supposed to be the min and which one's supposed to be the max. And I think we could do that by analyzing the direction. Okay, let's do this. So we have an angle A, or we have our point A, and this is the boundary, right? It can hit it in one of several directions, yada yada. But I think what matters is the comparison of that angle to wherever B is. Um, so we have to check if it's in that or that. And one way we can do that is checking. I mean, checking angles seems like the most straightforward, except for this bit. Um, so I guess if that angle is greater than 2 pi, then we just check. So there's a B angle, minus 180. And if it's, I guess if it's negative, if that ends up being negative, then we also subtract from 2 pi from the A angle. And if what is negative exactly? I guess if A to B, if our A angle, oh, yeah, if our A angle is negative and our B angle is less than 2 pi, right? So let's say our B angle goes this way. Then in this case, we just need to check that A is between 2 pi and 0 to determine that it's on the right. Right? Otherwise, if our, I mean, even if our angle was all the way over here, that would work just fine. So if our AB, thanks. Your test set works, but not the big one. Oh no. Are you still working on part one? I might get you now if this works on the first try. Um, yeesh, I don't like whatever that autocomplete is. So if angle 2A is greater than or equal to, no. Um, is it just greater than pi? Math.pi can be equal to. If it's equal to, this will work fine. And what are we defining here? This determines whether a angle is min. So let's say we're going clockwise. So about clockwise. Then we just do this check. And otherwise, oh, thank you, autocomplete. Otherwise, it's less than angle to bound. It's less than or equal to angle to A, or angle to bound is greater than angle to A plus math.pi. And there's a minus math.pi here. I'm not sure about that. Angle to bound. We subtract. Minimum value of angle to A is 0. So we just need to check. Oh, yes, we're going back 1 pi. Yeah, minus pi. In this case, we check in 2 parts. So we check, where is it? Okay, let's say this is our angle to A. So we're checking in 2 parts here. We're either checking that we're less than angle to A, or we're greater than angle plus pi. Okay, got it. Great. Oh, not remember math. I guess it's pi. There we go. Now if clockwise, if clockwise, then we check angle between, angle to bound. We're checking if the angle to the bound so here's our A. I guess this is the angle to the bound, and this is the angle to A, and we are checking if we're between, if we're going clockwise, then we have to be greater than angle to bound and less than angle to A. If it is clockwise, greater than angle to bound, no. We're looking at B angle. So BV dot angle. Let's cross that out. It has to be, what were we doing? Greater than the angle to the bound. So angle to bound, and then angle to A. Else, angle to A and angle to bound. Okay, minus like left. I think this would get it. Minus any like less than equal things I missed. What's wrong with BB dot angle? Not a member of point. BB is a velocity. Oh, right. Let's just put that on point. Or, I guess we take BV. Why is BV? Oh, B dot velocity, sure. B dot velocity. B. Oh, these are all 2D already. Okay. Let's just define an extension point. Extension B point def velocity, and we'd have the A10 thing, or angle rather. Angle. Okay. So we have BV dot angle. Hmm. We have other issues to fix. There's no YV. Oh, hold on here. YV and then ZV. I don't know how that happened. Day 24 was not found. Interesting. Oh, something that I'd never parsed up until this point. Okay. We have other fishes to fix. This is a match error. Oh, these are longs. And my point, convert them to points, don't I? And my points only handle integers right now. So I'm gonna convert these to longs. And I'm not gonna use a point class. So we have int replaced with long, 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 long. Not that one. In fact, we're not gonna use lat, so that doesn't even matter. Yeah, we just work on the x and y of these. 2int becomes too long. I mean, I guess velocity can be ints. That'll prevent me from making various mistakes. I'll stick with long. That doesn't hurt too much. Now we don't need this extension. And lat hail. We're not gonna use lat hail, we're just gonna use it. We're just gonna use our hailstones. Hailstones. Okay. AP, we have a position and we have a velocity. There are a lot of worrying warnings here to check out. And we still are getting match errors here. Let's take a look at that. We're not able to parse this. Oh yeah, we're getting a match error altogether. Let's look at our input. Day 24, 2023. So it is comma, comma. Oh, there's no comma here. Okay. 35687. I'm just going to try that before doing any debug because debug might take a while. 35687. Too high. 35687. Too high. Okay, some debugging. We'll check all those warnings. Man. But first let's try it on the example. Let's go back to day24.txt. We're going to save this as example. And pull out the example code here. Oh, that's our input example. It's only 4 hailstones. Okay. Well, we should get 2. And it probably doesn't have the edge cases we're worried about, but whatever. There's no dash there. Okay. We have a space 1 for what exactly? Ugh, okay. I guess we trim in case those are 1s. Or you know what? I'm just gonna change the input so I can handle it. The real input doesn't seem to have that issue with parsing. We still have an input string space 1. Oh, right here. Okay. Wait, we got 5? Oh, hold on. We have to like divide by 2. We look at every combination of 2 hailstones. Oh, what's the question? How many combinations of hailstones? Check their future paths for intersections. I should have just checked their actual intersection point. Oh, this was dumb. So I've checked if they will intersect. But I've done that without actually checking what their actual intersect point is. I shot myself in the foot for part 2, probably. But I mean, I could probably handle the math. So we have the intersection with the bounds. And then yeah, we have the intersection with the bounds for A. And instead of checking that they actually intersect, we just check if the path crosses it by checking the angle of our velocity and if it crosses that path. This might be a good time to try getting the actual intersection point because we're going to need that for part 2 when we're looking at the Z. So instead of trying to get this to work, but let me just take a look at what we're doing here. Long to double. Yeah, these are just a bunch of long to doubles. Those probably aren't my issue. It's probably a math issue, and I have to do new math anyway. I think I should just not debug this math. Oh, it's such a shame. But yeah, we can start over. I guess all you new viewers have some. You can see the problem from the start. I'm gonna save this as attempt 2. Okay, and we want the intersection between 2 points. Def intersection. And you know what? I'm gonna give myself a class for a hailstone. Case class hailstone. And it should have position and velocity. And it gives me an X method, which I guess that's cool. But intersection points might not be at those, so not sure how useful that is. Let's just make this a hailstone, a list of hailstones. And we'll wrap those up. Okay. And we're starting over again. Def intersect. A is a hailstone. B is a hailstone. And what we want is their intersection point, and we'll check if that's in the bounds. So this is a position. And now this is a chance to switch everything to doubles. What we might actually care about is doubles for precision. And then when we're like multiplying that by velocity and such, because a position might actually be a double, like an intersex position. And velocity can actually be ints. We lose too much precision on some of those numbers. I don't know. But our parsing is now 2 double. In fact, you know what? I can let Copilot do this. There we go. Okay. We have to get the position. Hmm. We could just take. We have to solve a system of equations. And I think the reason I shied away from this at first is because these aren't just lines, because they have one direction. Yeah, I thought so too. I'm starting over. Because my first approach, I didn't even actually get the intersection. I thought, well, I can tell if it is going to intersect that line without telling if it, what the actual intersection is. Um, and I can do that just by checking angles. But that's not going to help you with part two, and there was a bug in it anyway, so I'm re-implementing. Um, and let's pull out the whiteboard and see some math. We're not shying away from it this time. Okay, so we solve for the position of y, or the position of any point. It's going to be starting point. So the start, and these are points. You do these for both x and y. Plus, or we do it in a different order. So let's say the position equals velocity times time plus the start. And now we have to solve for the position as the same. So start a plus velocity a times time. I guess the time doesn't matter here anymore. So velocity a, we'll figure out what to do with the time. We'll keep drawing it in here. Velocity times time equals SB plus velocity times time, velocity B. The thing is, these could be different times, which means the velocity sort of doesn't matter. I guess the viable positions. What to do with time? And we're solving for we want p. So we have a time such that they're both the same. It doesn't matter. Let's look at like all viable positions, and we draw a line. So let's draw the line system of equations for one and another. So let's say we have a point. Let's say we start at 1, 1. Let's draw these out. 1, 1. And then we have a velocity of like 2 over 1. So it's going up 2. So 1, 2, right? So it goes up 2 points over 1 in that angle. And then let's say we have another velocity. I still don't know how to handle like this not being an infinite line, but we'll figure that out. I guess we could look at that intersection and check if it's in the right direction given the velocity. So let's say we want to get to this intersection point here. Let's say we'll call this A. So this is A. If it A is 1, 1, then it should be 2, 3. So if you wanted a 2, 3, we could have a point like this here. So B, which starts at 1, 2, 3, 4, and up 2. And the velocity is negative x, negative 2, and then positive 1. And let's write equations for the full lines and figure out like how to solve the equation. Excuse me, how to solve the equation, and also how to handle the fact that these lines are infinite. So the A line is going to be the y value. So y equals 2 times x minus 1, 2x minus 1. And how do we get that from the point? Well, we'll figure it out. And then for b, we have y equals negative 1/2 of x. So there's our slope. And I guess what would the intersection point be? If this is 1, 2, so 1, 2, 1, 2, 3. So this intersection point is 2, 3. If it keeps going that way, we have 0, 4. So this is plus 4. Okay, and great. Y equals 2x minus 1. Here's our y-intersect. How did we get our y-intersect? Let's think about that later. Now, to solve for, we solve this for x, we solve this for y. So 2xa minus 1 equals negative 1/2 xb plus 4. And actually, xb, xa doesn't matter. We're just solving for the same x. So let's add them. Right? I guess we take, this is the coefficient for xa, which you can calculate at some point. But we would subtract the coefficient for xb. So 2 plus 1/2 of x equals 4 plus 1, and x is going to be 4 plus 1 over whatever. So we solve those equations. I think at this point, let's say those are going in the opposite direction. like inequalities, right? Let's say we had these two lines. I may just think we just check if that point is on those lines, and we'll cross that bridge when we get there. You leaned on maxima hard. Yeah, I need more tools in my toolbox. um, I should be better at linear programming, or I don't know, like some graphical programming tool, or honestly just a library that handles this kind of stuff. But library feels like it's outside my rules because I just want to use a Scala standard library and anything I write. So I'd have to write this stuff up. Okay, so I'm gonna move this to the right, um, so that I can look at it as a cheat sheet. First, we have to determine the coefficients. Um, given, do I get enough screen? Okay, we're just gonna shorten this so we can see everything. Okay, so A's x coefficient. Well, A x coefficient. Um, and it's gonna be a ratio 2/1. So A dot velocity dot x, A dot velocity dot x over A dot velocity dot y. And I think we want those to actually end up being doubles. I'm just gonna change them to doubles up here. Double. And we'll replace 2int with 2 double. Okay. And then AY intercept. AY intersect. And A dot position dot x. Yeah, exactly. We just solve wait, hold on. So we have our position. We're basically plugging position into here, right? So position dot y, ax coefficient equals the coefficient, the x coefficient times x minus the whatever, minus the intersect. And we switch that around. We end up subtracting this 2x bit from the wait. We're solving for this from y. Yeah, a dot position dot y minus. Okay, I mean Copilot's just right there. I don't know why I'm checking. It feels like cheating to have Copilot do my math homework for me. Okay, now we have a little bit more room. So from the system of equations, what are we trying to get? We're trying to get the intersect points. So Val, I guess we need the bx coefficient, yeah, and the by intercept. Okay, and then now we have to get the x intersect or x, and it is just subtracting. We've done this math already, divided by the coefficients on the bottom, right? This coefficients that move down here, and val y. That is simpler than I expected. Why? Divide, divide. I don't believe that. But we can test it. So this is still on the test data. So we can do hailstones. Or you know what? We can return position XY. And then Z, whatever. We can say 0 for Z. Now we take our hailstones. Wait, are we compiling? We have other issues. Where is this issue? Oh, we don't need this colon here. Okay, we are running now, right? And hailstones at combinations 2 that count. Oh, let's do a match. So we have an A and a B val intersect, and then we have those 2000 and 4000 numbers. So let's just open up day 24. We've written them in there somewhere. Min bound equals here. Oh, again, we're not handling. There should be an option of position. But right now we should get too many answers. So let's do that, knowing we'll get too many answers and we'll have to fix it. And we check if the intersect is within the bounds. So I dot x is greater than equal. Or, you know what? I want to phrase it differently. Min bound is less than 4. Yeah. So that is what we're looking for. Wrong number of parameters for intersect. Wait, what? Oh, wait. We're matching on the list. So case list of A, B. Min bound. Double definition. Val min. Oh, we have him. Oh, hold up. We are writing the code in the wrong place. Okay. So now we switch to this try 2. We have our min bound, we have a wipe, our max bound. This is our try 2. Oh. It is all very defined. Okay. And here we actually count 0. So we were actually hoping to get more. Let's pass into hailstones and check this. Let's do exactly this example I'd done. Val A equals hailstone. Precision, we're just going to say 1, 1. 1, 1. And velocity is 1, 2. And val B. Oh, the bounds are different for the example data. Okay, so I'm just going to override it here. Thank you. Thank you for that back here. Yeah, I'd forgotten about that. Where is it? It was like 7 to 27. Yeah, at least 7, at most 27. Min bound equals 7, val max bound equals 27. now we get 5. Interestingly, that's the same answer we're getting in the other. And I think it's because the other didn't actually handle the case where the line wasn't infinite. So that was the only problem with the other one that I'd done. So now it's going to be an optional precision. Because we need to do a check. Let's just make this sum for now, and we're going to define a new function. Def in path. So P precision, and then hailstone, H hailstone. You know what? Just trust that. It's wait. Time. You know, I don't know about that, but so option not when. Oh, let's define the position separately. Val P equals this position when in path P of either hailstone A. So just say A and return P. So now we can do intersect AB dot, does there exist an I such that all of this holds? Exists. Okay, let's go back to testing things on our example here. So let's get the intersection of these two. 4, 2, negative 2, 1. 4, 2, negative 2, and 1. Now let's get the intersect of those two. Intersect of A and B. And it gives us a none. Let's print line P anyway. Print line P. Rate 2.4. Oh boy, those are not values we wanted. Right? It should be 2 and 3. I blame floating point arithmetic. Or maybe this right here. Okay, for now, let's just run some P. We're not going to consider the in path. Let's figure out what's wrong here. I think this val y line, I didn't actually check myself. Well, actually, the x value is also wrong. Because x should just be 2. Right? And our math for that brought us out. So solving for x, 4 plus 1 over 2 plus 1 half. So that's 5 over 2.5. Oh, which is actually 2.5. What? Did I do this wrong? Because if our A has x velocity 1, y velocity 2, it'll go there after one step to 2, 3. And if our B at 4, 2 has x velocity negative 2, boop, boop, And y velocity 1 should also go to 2, 3. Right? Oh, I feel like I'm gaslighting myself here. Okay, so we just set like y, we just set y is equal and solve for x. So we have our system of equations. I'm gonna print our coefficients. Um, okay, ya. And then we're gonna do the same thing for b. Okay, and what do we get here? Ya equals 0.5 times xa plus 0.5. Ya, wait, it goes 1 across and 2 up. The slope should be 2. It should be 0.5. And it's plus 0.5. Yeah, that's kind of very backwards. And then y for b. So a is this. The ax coefficient is actually a dot velocity dot y over b over x. And then the ay coefficient, or the ay intersect, should be, we're saying y minus ax coefficient. Yeah. So y, we're solving for this here, -1. We should get -1. And that will be, plug in y into there. So the y position, a dot y minus 2, minus the slope times x, minus x coefficient times a dot position x. Okay, so that looks right. Okay, 2x minus 1. Wait, it should actually be, yes, it should be -1. 2x minus 1. Great. Okay, so this should be y over x. I don't know if that's my fault or Copilot's. It should be half x, or negative half x plus 4. And now the intersection point is correct. Okay, and let's check. I'm going to check in path by inverting these velocities. So can you just invert both? You have to swap two. Yeah, you can invert both. Negative, negative, and then this becomes positive, and this becomes negative. So that should give me the same point, A2 plus A2 and B2. And we'll get the intersect of A2, B2. Okay, that's the same answer. Now let's do this with the in-path check. And they both get none. So our in-path needs to be fixed. So let's do an in-path of, I guess, A. Yeah. So A, we'll look at a piece that goes up there. We'll look at a piece that goes to negative. So 2, 3. In-path, position 2, 3, O with A. and then position, not 2, 3, but 0, -1. 0, -1. That should be true and false. Um, I'm running on time, so say true, false, where A is, let's just put it up there. Hmm, I'm gonna delete that for now. We're gonna do this math ourselves. So I guess like if the x is positive, oh yeah, it should just be like greater. Um, let's do this. If h dot velocity, well, if h dot velocity dot x, no, we'll do two methods. So val x in path, and then if the velocity is 0, then it has to match. So if h dot velocity dot x is greater than 0, I don't think min bounds matters here, so that's wrong. If h dot velocity dot x is 0, then h dot position dot x should be greater than or equal to, should be greater than or equal to, or actually p dot x. So p dot x should be greater than or equal to h dot position dot x, and we don't care about those max bounds. And else if less than, we just do the opposite. Less than or equal to h dot position dot x. Otherwise, the positions should match. And we'll have a line path. At this point, autocomplete should know from that example. There we go. And then we just return x in path and y in path. Okay, now our tests, we get true and we get false. Excellent. I'll just now we count 3 here. I don't know what edge case that is. I'm just going to try. I'm just gonna try this on the real data, and that's probably gonna be close. We can comment this out. 16684. Let's try that. 16684. Still too high. 16684. I believe it's too high because our last one overcounted as well. Okay, so we have intersections. The intersections seem to be working properly. But we need more examples here. So of all of these, let's look at which ones do intersect, or which ones it says intersects on the example, and try to figure out what's wrong there. Nope. Do I normally name them with X? I think I normally name them with X. X, yeah. I don't know why I changed today. I'm renaming this as -X. There we go. So instead of a count, we'll do a filter, and for each print line, Uh, Filter these cases, then dot for each AB and AB intersect. So we'll just also print line A dash. And let's look at our output and compare it to their work through of the example. Is there a problem here? Match may not be exhaustive. That's fine. Are we in the wrong? What did we get here? Let's kill that. There are issues here. They're just non-exhaustive matches. So we're going to look at the worksheet output, scratch. Okay. This didn't print anything. Oh, of course, we didn't change the bounds. Right, we get the answer 3. Let's look at what those 3 are. It says it intersects at those points, and all those points do appear to be within the bounds that we desire. Hmm. Hmm. Okay. I'm not going to stare at that too long. What I want to do is compare with this read through. So Hailstone A, 19, 13, 20. These will cross inside. Great, those will cross. So the first one's correct. The second one is correct. It's one of ours, 19, 13, 30. And now let's look at 2025. 2025, 34. Right here. Hailstones crossed in the past. For Hailstone B. Like these other crossings. 1, 2, 3, 4, 5. Yeah, we can check these other crossings by removing that filter. So option not when. And then we can note an in path or something. So we're just gonna say P or some P. Let's put this in Scratch too. Okay, there are 5 intersections in both examples. So you have the 14, 15, you have 11, whatever. 6.2, -6 and 5. We don't seem to have these. -2 and 3. We have other points, but let's see what they are of. So this is 19, 13, 30. 19, 13, 30. Hailstone's paths crossed in the past for Hailstone A. So they did cross. 19, 13, 30 did cross. but it is in the past. That intersection is probably correct. These never intersect. Well, let's look at from the top to the bottom. So 1913-30 with 1819-22, they cross inside at that area. 1913-30 with 2025, they cross there correctly. 1913-30, and then my third one here says they cross in the past. 2019. So this is supposed to pass to cross. So let's look at why that's not happening. So that's the first hailstone with the third hailstone, isn't it? 825-34. Nope, nope, nope. It's 1231. Oh yeah, the fourth hailstone. So index 0 with index 3. Let's try that. We have our A and B tests. Cool. Let's do the intersect of hailstones 0 with hailstones 3. That's the first one that doesn't quite match. 6.2, 19.4. Oh, I do have an intersection for those, right? I'm gonna go back to like printing what it would be, and doing an option because I want to know if it also says in path. So this gives us a sum. Why doesn't it show up in here? So what's on here? Oh, this is listing positions for, it's also listing potential positions. Yeah, potential position, and then that. And for each of the combinations, I do this for each of the combinations. Some of these, oh, position infinity. Yeah, and infinity is going to be the parallel case. But why does that print so many? Because for each of these, we do end up printing. We print the hailstones, we print their intersection, and we print a triple line. It seems like triple lines are missing, or these dashed lines. Okay, well anyway, we did cross properly there. Let's just test all of these. So hailstone 0, that should be none. That should be none, but it's some. So that is wrong. We'll just say like be none. They're problematic cases. And hailstone 0 with hailstone 4. The 2019-15, right? 1, 2, 3, 4, 5. Or 2019-15. Hailstones paths crossed in the past for hailstone A. Oh, wait. It has to be in path of both of them. Okay. Yep, in path for both of them. When in path PA and in path PB, then we do P. Okay, so this now should go to none, right? Because it's not in the path for one of them. Uh-oh. Okay, there should still be none. 6 to 19.4. This crosses a path, so that's none. So that's correct. You know what? I might as well do all these examples that we can see them passing. Okay. This intersects at 1415. This intersects there properly. This intersects there, but that should be... Oh, that's outside the test area. Okay. Yeah, that's outside the test area. That's fine. So that should be some. So that's correct. That'll be filtered out. Actually, let's just see what our answer is giving now. 2. It's not giving 2. It's probably correct now. We just fixed the thing. Let's comment those 2 bounds out. And get rid of this print lining for now. And this print lining. And I guess all of this testing here. Okay. What's my answer here? Val adds 1 equals that. Oh. Do we really get 0? This is for the full... Oh, right. We haven't changed it. There we go. 13965. Oh boy, this took way too long. 13965. Continue part 2. You tapped out. Was a nice run. Oh, you know what? Yeah, 3 hours of sleep. That'll do it to you. I see black deep. I missed your messages. I think my overlay is broken right now. Let me just give it a refresh and see what happens. Oh, you know what it is? Here we go. Let me give it a quick test. They say use the right tool for the job. Tonight you lean on Maxima hard, right? Yeah, Python does have a library for anything. And you reminded me about the bounds. Yes, thank you. I appreciate that. And there we go. Okay, we're back there. Now we just throw in z's, right? On further analysis, it doesn't seem like any hailstones will naturally collide. It's up to you to fix that. You find a rock on the ground. While it seems extremely unlikely, if you throw it just right, you should be able to hit every hailstone in a single throw. Yeesh, what is this? Okay. We can propel it at any integer velocity, now including the z-axis in your calculations. You throw the rock at time 0, where do you need to be so that the rock perfectly collides with every hailstone? The rock won't slow down or change direction when it collides with the hailstone. So we need a 3D line as in the path for all of these. You know, I can straight up delete all of these. I'm happy with that. I'll leave this test code in here. And I'm just going to do a quick commit. You know what? We're going to overwrite day 24. That's what we'll commit. Day 24. Okay, 2023, day 24, part 1. That's all stream. Now we go into this. We need a line in the z-axis. You achieve this by moving to the positions 24, 13, and 10 and throwing the rock at velocity, whatever. Do this, you will hit every hailstone as follows at specific times. Okay, so our in path, if we make our in path include the z-axis, no, not quite. We could do this in two parts. Let's look at it like a simplified XY. So let's say we have a rock going here at some velocity and another rock going here at a greater velocity. And um, and let's say like this is our correct line, right? First we need to find that line, and then we need to find the timing. What I could do, okay, well, like a dumb brute force way to do this is try to solve, well, no. We can't just rely on their velocity and the time uh, without also thinking about the time right now, right? If you just think about like when it hits a line or when they share a line. So they might, let's say they might share a line right now. They all have like different velocities. Let's say we go there, and we go there. At the next point, it's going to be that kind of a thing. What happens in the times before? They all share a line, but not at the same time, right? Let's say we had these three all have the same velocity, and these would share the same line at different times. How do we figure out what this line here is? Right? Oh, Alka, thank you for the raid. Thank you for the raid. My part 2 secrets. Well, you might be ahead of me on that right now because part 1, I did an implementation that didn't use an intersection. It just used angles. And it's like, okay, between this angle and that angle, it will intersect at some point. And that made it hard to check whether it's actually in the box. So I was getting like the 5 intersections, but not within the box. So I started over again, and I thought, okay, let's actually find our intersections first. And I avoided doing this because they were like partial line, whatever. But it turned out the math was easy. It's easier than like the arctangent stuff I was doing initially. So that was like an hour and a half wasted. So in the next hour after that, I just finally found out, okay, this is how we get the intersect. And now I'm thinking about part 2. So if these coincidentally are already sort of in a line here, if we don't consider time, right? The timeline just sort of gonna have like a different slope, and that's only if they have the same unit velocity vector. We could group them by like unit velocity vector. I wonder if any of them have the same. And that could give us a hint, right? Because it'd be very easy to figure out. Well, I guess we could have different speeds of throw, right? If this if these are all moving at 1, then it'd be this line, right? But if our throw had to move at 1/2, then it'd be like this line right here. Um, yeah, oh no, indeed. I am, this year, I've been the king of wasting time on not the right problem, but lesson learned. I want to have some sort of checklist next year of things to remind myself of that can prevent me from wasting time. I think I need, we'll see. I'll do analysis. One of the big things, one of the reasons I'm doing this advent code this year and recording it all is so I can analyze the videos for any kinds of mistakes. I've already partially analyzed some of them and talk about them. I'll make YouTube videos probably. Occam's razor, indeed. Okay, so we could use these that have the same unit vector to find a relationship between speed and I guess line angle. Hmm. I feel like the intersections, the intersect method we did from part 1 should help. Um, I don't want to do equations in 3 directions. Okay, what else is there? Oh, we go. Day 24 in 2021 was also really hard. It was a reverse engineering problem. It took me. I went back to it over and over again over the course of the day before I finished it just before midnight. Um, let's look at this again here. Oh, oh no, that is not helpful. I can't do this with a pen. Let's look at their example. See if we can notice anything about this. So if we threw with that, they're just sort of giving us one. Move to that position and throw the rock at that velocity. At times 5, 3, 1. Collision position. And we could do like a move function. Let's define a move function because it'll be helpful, even as we're like testing and developing into. So hailstone next. Oh, it's right here. But I want like move a number of times. So we'll then do def move time. And we add the coordinates together for the answer. It's probably gonna be a double. Was this input like carefully crafted so that there were no floating point errors? Because I'd be like super worried about that. Okay, so position plus velocity. Oh, I guess you can add positions. But we want to be able to multiply velocity. Def multiply. Yeah. So position plus velocity times time. And it's still going to have the same velocity. Mm. And I mean, I guess at this point we do only care about the position. So if we wait, what is a new position basically? Let's make this return a position. Yeah, okay, that works. For 1 nanosecond. Wait, really? I guess they're saying nanoseconds here. 2 nanoseconds after that, it's just 3. Um, okay, if we were solving this as a system equations for like x and y, let's see. We have an equation for a stone, and maybe we can solve that in terms of an x and a y, or an a and a b. So let's say maybe we use our same a and b example. What was it? This one here. And I guess for this one, it would be like time equals 1. So let's do another example. Oh, and they don't even need to intersect with each other. They just both need to intersect with this point. So honestly, you could do this for any A and B if you're just doing an A and an A and a B. So let's look specifically at these examples here. Oh, I don't like them. They're so big. And just solve for 2 of them. Right? 1922. Fair enough for the real input. Yeah, let's just do this bottom one that goes at 1. So let's say A. Oh, but then we have to solve for their like XY equations again. I think we can ignore Z now for the and then just generalize later, like for the purpose of developing. I'm gonna copy these into my sheet, and I can print out their equations using my intersect function. So I'm gonna uncomment those print lines. Um, and let's make my parse function separate so I can just copy paste lines directly without having to worry about switching back and forth between the example and whatnot. Oh wait, not found precision. How? What did I change? Oh, we're missing the colon here. We can multiply a velocity. Yeah. Oh, okay. Right, you can't add a velocity to position. Let's just make a new position. Yeah, that's it. That's fine. We don't need this multiply function here. And let's make parse separate. Object hailstone def parse. It copies my code. And then here we can just do hailstone. Oh. Okay. Stone dot parse that string or input.map hailstone.parse. There we go. Okay, and let's pull out some examples. Let's go to where we define intersect. And let's just look at the intersection of two hailstones. I'll just call him H1. Hailstone dot parse this one here. And val H2. Oh no, I didn't want that one. We want this one that intersects at 3. H2 is going to parse a different string. There's this one that intersects at 1. Okay, now we can get their equations, right? By taking intersect. Yeah. Intersect H1, H2. So 1xa, so 1x plus 1. Oh, interesting. And that's just for their x and y coordinates. So for a, we have y equals 1x plus 1. What was it? Wait, the intersect down here. Y equals x plus 1. And for the other one, we have negative 5x plus 119. Y equals negative 5x plus 119. And I guess while that does give us lines, and where's their intersection point? They have no intersection point because it's going to be like in the past, right? Maybe that's not a helpful example. But let's say that, like, we did have 2. Do they even need to intersect? They don't even need to intersect, right? They could be parallel. Look at what their intersection point would be by uncommenting this line. It would be at 19 and basically 20 and 20. So negative 5x, this is like a heavy downward slope. And it'd be like up here kind of a thing. So let's just pretend for a second. And then now they both intersect the line that has a t dimension. I think we need to go back to having time in the equation. That was a mistake. Where did we have time in the equation? Here. Okay. So if they intersect with time, so we need to check like the intersect with time considered between a rock and a hailstone. And how many rocks does it take to narrow that down? Right, let's say there's, so given a bunch of parallel rocks, right, then you have infinite because that angle could change. But given rocks that are going in like different directions, let's say we have a rock going here and a rock going in that direction. So I'll just highlight the position with a dot. Um, well, actually, this is never going to work unless this other one is moving faster. So let's make that arrow longer. Um, and let's do another one that's going even further in that direction. Right now, does this narrow it down? Let's say this is a slope. This is like straight down. This is 2, and this is over 3. Or -1/2 and -1/3. So we have 3 slopes. They're all starting at the same height. Um, so they start moving like this, and then 1, 2, 3. I'll be on that line at the same time. So if we're moving here fast enough, this will narrow it down to 1. So any 3 points, we just solve a system of 3 points, right? If they all must, because if they can only meet on one line, then so is this like, these are equations of 4 variables, right? Time x, y, z. Maybe it's just time, position, velocity. Because p2 equals position, position 0. I guess just a new p. Let's just say p prime. P prime equals position 0 plus p0 times some time. We'd have to have a rock that's going down here and then moving fast enough to eventually catch up with like this one down here, and then moving fast enough to catch up down here. And if we're just looking at 2, we're just looking at 2 points, we're going to have a variety of things that can happen. So we could decide on the time between those two, right? Let's say we decide it's going to take 3 seconds. Then this moves down once. This moves over 1, 2, 3 times. I'll just mark that with points. And that, so fixing time fixes our velocity. So which is to say there's a relationship between time and velocity. TV relation of some sort. And then once we throw in a third into the equation, and we have to intersect with that, it doesn't necessarily give us a starting, well, okay, it does give us a starting position. We could probably choose between multiple starting positions. So if we started like all the way back here, well, hold on. If we, so given a time, our velocity and our position is fixed, right? We'd have to start back. So this is like 1, 2, 3. You'd have to start back. Let's make this a cleaner line. So if there were 3 seconds in between these two, 1, 2, 3, then that determines how far back we have to go. Right? If our velocity is determined by time, then that also determines how our position. And if we decide to throw it, if we decide we wanted less time, right? We wanted just 1 second between these two. then that would also determine our position. It'd be something like here, and it would meet. Where would it meet? So this is 1 second. Hit the first one at 1 second, 2 seconds. Oh, hold on. That's not completely true, right? I'm always assuming there's 1 second before we hit this one. Okay, so if there's 1 second before we hit that one, if we decide that this is 1 and this is 4, and there's like 3 seconds between, then position is determined. If we decide that this is 1 and 2, position is also determined, right? Position and velocity both. So if we fix time, if we fix both times, right? If we decide this is like 2 and 4, it would still have the same velocity because of the time gap is the same. Um, or right, so let's say we had 1 and 3. Let's say 1 and 2, right? 1 and 2 is this one here. That determines the position. If we decide it's 2 and 4, we would still have the same angle, the same velocity, right? But it would happen. No. This would move further. It'd be something like that. It has to catch on the third now. So that determines a different velocity angle. Yes, in general, x equals x0 plus dx. Yeah, I I got that. That's this right here. Um, okay. So we have our rock equation. We have all of our other equations. We want a solution for our rock equation. So we want to figure out what's rock 0. So say position, rock 0, say PRO, and we want velocity of rock, which is always going to be fixed. So plus velocity of rock. These two things we need to determine. And we can figure that out by setting P prime to other other potential values. So PR0 plus VR times T, right? And let's say we have our two other things. Let's what happens if we set this rock equation to match another equation? So let's say just this equals, let's just call one of our hailstones A. So we have PA at 0. Plus VR times time. So we would be able to solve for VA times time. And in this equation, the time has to be the same. The time has to be the same too. So if can we simplify this? We are already given this. We have to solve for PR and VRT, or rather we just need an equation for them. And then we do this with multiple different values to narrow that down. But it'd be a different value of time. Well, let's solve for like PRO. So like get different values for this. And this line will kind of just be like repeated. And since we have 1, 2, 3 variables, I guess we need 3 equations. So we have how do we relate that? There's like a time delta. Do a time delta between 2. Um, let's just call this like T1, right? These share the same T1 value. So PR0 would also equal like, well, let's write this down. The velocity of rock, um, T1 minus PA0 minus VA T1, and then we'd have another equation, and we could set these equal to each other. So PRO also equals VRT2. I guess 2 is just going to match up with B. So we have PB at 0. I'm going to start dropping the zeros because we're only really talking about this one position, minus VB times T2. Okay, and then now we have this equal to this, and we need to solve for, we want to solve for VR. Then we could say VR equals, if I was writing this in Copilot as comments, I could probably autocomplete everything. That's probably what I should be doing. How do I take VR out of both of these? What is it in terms of these? And a T1 and a T2, and a T1 and a T2 still need to be solved. Make this bigger. I need more space. So we have VT minus P minus VT equals VT minus P minus another VT, and these T's, it's going to be like TA, PA, TA, and again, B, B. And then these like VBs, we don't need to think about them. They're just constants. This is unknown. This is unknown. And this is unknown. Oh, wait, this first V, yeah. And let's start by like putting them on the same side. So v minus v equals p plus vt minus p minus vt. I'm just gonna drop the subscripts for now. And solve for, wait, these are vt. These are both vt. So now we have v equals that whole thing. I'm just gonna ignore the sign. That whole thing over t minus t. Those t's being ta minus tb. Again, this is like a ta tb. I feel like I'm doing too much math. It shouldn't be necessary, should it? Oh boy, it is 3 a.m. But I think I can get this in an hour. I really want to go to sleep by 4. But that is my limit here. It is all math. So you have a way to solve for like v, and now if we took like another system of equations, right? If we took this thing, I'd be like, oh, I'm gonna copy paste this. Hmm. Hmm. Okay. And now the A's and B's are different. And we can, but we're adding more T's. We're adding more different T's. I don't like that. But you know what? We have a relationship for B. Given 2 points, then whatever this time ends up being. Um, so we have V given 2 time points. And given V, we can determine what P is. Can we determine what P for the rock is? Just to A and T B. We can get P from TA and TB. Right, then we can fix TA, fix TB. You don't know how to solve the system by hand, which is why you threw it at Maxima. You know, right tool for the right job. um, oh. Right. If we start adding more points, we start adding more variables, more of the t's. But we want to narrow down these as well. So then we're able to get v, an equation for t, v given 2 times. But that also probably fixes p rock, right? Yes, exactly, because p rock would be related to t1. So given an option for 2 times, we can get velocity and I guess what we could do, take two hailstones, any two hailstones, plug in some times for that, and then just check. Oh, no. That space is going to be too large. Mhm. So we can get P and V given a TA and a TB, right? Because we could solve just TA or TB. Because, I mean, we have a V. We have a V right here. I drew these two equations together. It's not actually the case. We'll just separate those. We have that. And then we have this equation. And duplicate it. No, duplicate it. I guess for copy. Get the position at any given time. And we could solve for time equals 0, right? Given V, which we can get from 2 timestamps, we can solve for position of rock. Oh, no, we need, so given VR, set t equal to 0. To get PRO, I guess P and P would just be equal. F time equals 0. Oh, and all we get. No, that that doesn't work. I'm pretty sure 2 points that can determine a position. Well, yeah, because of delta to 0, it determines the starting position, right? If we're saying we have 3 seconds before here, that completely determines how far back we have to go. Because that determines the velocity, and that velocity and the time remaining determines the position. Okay, so we have that. Now, if I added a third hailstone in here, man, I wish I was good at linear algebra. I really do. And Illyri, thank you for the follow. So let's say we just introduced a third timestamp. Given times for 2 things, can we get a relationship between two rocks, and can we get a relationship between those 3 times? And if we can determine a relationship between those 3 times, this problem. Is there anyone here who did solve it with a with nah? Get a third equation in there. Third rock. And what do we want to solve for here? TA and TB. A lot of these are constants. Oh, you know what? It might suffice. Mm, yeah, let's just replace some of these B's with C's and see what happens. Yes, but only setting up the equations and letting, yeah, CAS system solve it. Okay, let's fix A, and let's just add in SC. So like the rock should share velocity, and if it does, what can we find out from here? There's now a times C. Say we knew a TA and a TB. What does that tell us about a time C, like time C's relationship to those two? And that gives us more constraints on how TA and TB should behave, right? Yeah. Okay, let's solve for time C in terms of TA and TB. Mm, I guess we like, okay, we have to like multiply. I'm just gonna copy paste this whole thing. So and you're gonna move the bottoms. Okay, we can copy that. I guess there's no cut key binding. I'll tell you, this Microsoft whiteboard is just so counterintuitive to me. And I guess we could just ignore underlines. You know what? I'm gonna make this nice because we have to think about it. We have to stare at it a bit. So that's our TC. The only special thing that we know a solution exists, and that means you don't need to solve for all the hailstones, just enough to get an exact solution. Yeah, right. You only need 3 or 4 hailstones, I think. I agree there completely. Um, and then there's this whole thing going on. We're gonna multiply that across. You know, I should just multiply in one step. So we have EA guess TAPA. And it's multiplied by that whole thing. But TC, like we want to isolate. Okay, so TAPA plus TA. Oh, some of this can be simplified. So TA V, wait, V? Okay, yeah, that's VA. VA TA. Velocity times time of A should just be position A, right? Oh, hold on. It should be the position at that time. It's not gonna be PA. PA is a starting position. I don't like this. And I should maybe be writing this in the text editor instead of drawing it. You can solve for XY plane first, which probably leaves you with an unknown that you had to solve with Z or S. I mean, let's take a step further. Like, what if you just solve for X first, right? Solve for one axis. Like here in my drawings, I was thinking about just X and Y. But if we can find a relationship, and you know what? With so many different X values, we have all these X values. Yeah, let's do that. Let's do that. That might get us somewhere. With all these different X values, is it possible that just X is enough to give us good time examples? Or are there going to be infinite solutions? Well, they are going to go in, they have to go in some direction, right? We're either going to throw the rock from like above down this way, in which case the velocities are the ones that are lower and far. So if they share the same X, then this has to have a greater velocity than that. And I have this pointing straight down. These are going to be the X values. That's pointing straight down. This is not meant to be an XY thing. This is time. And this is whatever X they intersect. X intersect. So I can normalize this. I can just say, you know, it's down, no matter what. So anything further down, same whatever, is going to have a longer vector. Anything further away is going to have a longer vector if it's the same thing. And you know, even longer vector if it's like further away. We can look at like the range of X values. Or we could sort them by their X values. These are small X values, these are large X values. And this is X increasing over time. It would be kind of helpful if we had. There are parallel rocks, aren't there? Okay, but we had two in the X direction. We approximately solved it using minimization, then fine-tuned a bit. I mean, I guess it could be like some sort of binary search-ish type thing, kind of like a Newton's method for calculating the square root. Mm, yeah, if we sort these all by their x and look at their velocities, what will we see? Will we see enough that the intersection line has to be determined? I think that might be the case. We can solve separately for x, y, and z. We don't have to do but we're sort of back to like doing the same PV, P equals Vx or x plus Vt. I suppose we could determine a range of possible t's. If you look at the difference between this and this, right? Like the distance and the velocity, it's going to have to be an x that is further in that direction. They all have to be roughly. You can't have, I mean, I guess you could have x's that are decreasing, right? We could have x's that are decreasing. What is this axis exactly? If it's up, it's a lower x value. And then with time, I guess it increases its x value. So there could be a very high x value. And this is if we're going to throw it with an increasing x. If we're throwing it with an increasing x, then we're going to probably try throwing it this way. And things with higher x values. Oh, wait. Things with higher x values in the same position can move slower. Okay, let's start this again. So we have a rock. We have a rock, and here x is increasing. So let's just say, it starts at 0. 1, 2, 10, etc. And if we have a rock that's at -1, so this would be negative. Well, this would be -1. X would have to be increasing at some rate. If we had a rock at um, we can have multiple rocks at -1. I think I actually want to have velocity going down. Let's say the one, if its x is increasing, it hits there. We have another one. If we had another one with a higher velocity, increasing over time, 1, 2, whatever. This is increasing over time, but faster. Yeah, we could sort them by velocity. I'm gonna look at these. And since some are negative, some are positive, they have to meet in the middle, right? So look at our hailstones. Just do some playing around with the data. Um, H, we're gonna get H dot position dot X. I think we care more about their velocity. We're gonna sort by velocity. H dot velocity dot X. And then we're gonna sort by um, 1. And let's print line that for now. So we have all these velocities. These have to meet somewhere in the middle of all of that. So this is a high X value, I suppose. And it's increasing very rapidly. And it's just decreasing very rapidly. It's between those two. Let's look around 0. Okay, there's no zeros. But here we have a -6. Oh, wait, -6 is a velocity, right? Moving inwards out of radius 6 from this, like 4e14, 1e14, moving upwards. So we know it's like in between there somewhere. This is also moving at -6. So the position there is smaller. Um, if they're moving at the same rate, I guess that skews. The distance between those will always stay the same. Let's look at just that kind of example. So suppose we had an x here as moving at that velocity. You have an x all the way here, moving at that same velocity. And they're going to hit the same point at some point. So let's say like if they both, oh no, they're not going to hit the same point. They're going to hit at different points. This moves over like at a rate like that. This moves over at a rate like that. If they're really far away, you might have to move really slowly. There's like 2 million between those two that are moving at a rate of 6, right? A very, very large number. 6 and 6. They're 2e14. And it could be anything, right? If it's 1 second, then this is gonna move very fast. Like that fast in the negative direction, I suppose. It's impossible for it to be like a 0-second gap. But like if it were allowed to be a larger gap, then it could end up being something like that. The larger time gap means a smaller velocity, of course. Let's take a look at them sorted by position. Whoops. What if I swap these? That map, that swap, and then sort by one. Okay, positions first now. I don't think there should be any with the same X. But there are some high ones. Okay, so these are some small ones, little ones. And their speeds vary. Like this goes negative. Like how does that work? If this is going positive. The next one's going positive in a very fast speed. Right, so we have a bunch of rocks at a similar X position. Yada, 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 yada. And all of a sudden, we have one that's going positive in a very fast direction, and we have another one that's going like negative in a very fast direction. And what kind of stuff are they surrounded by? So this negative 107, 172, and then like we have another negative, and then we have another pretty big positive. Like it's gonna be alternating. And I don't like this. Hmm. What we could do is look at time and look at X. All these pass at different times. Like we might have to hit this first. If our X has a positive velocity, we might end up hitting this first, this next, and eventually catching up to that and that. And, oh, you know what? We have bounds for velocity, right? If there's a negative whatever velocity, and that one's going like, let's say we have negative 300 and positive 300. And we are going in this direction. We have to be at least positive 300 to be able to catch up with this. So we have to be higher than the max velocities. Hmm. Oh, Brett, you're talking about yeah, given the guess of P and V, you know the T's by some linear algebra. Yeah, if you guess P and V, then you can know the T's, and you define that your loss function. Okay, so that's kind of like that's kind of like the Newton square root approach. And We could keep improving. Yeah. So let's do that. Give it a guess for x, and then we have a bunch of times that we would hit each of these, right? And we already have some bounds for x, for like x velocity. So we have a bunch of times when he would hit each of these x's, maybe. Um, okay, so let's say we have different times for different rocks. Well, now we do that along each axis, and like the y-axis time is going to be different from the x-axis time, and the z-axis time is going to be different altogether. And then we could use all of those deltas to help us move further in the right direction. Okay. Yeah. Loss function, exactly. Let's do something like that. Um, okay, so def foo. We have a guess. Um, and as long as we have some way to improve upon that guess, um, let's see. We'll call this deltas. So given a guess or rock, and this could be, we'll call it rock guess, and it'll be a hailstone, which is say it has position and velocity. Mm. Do the x, y, and z have the same times? Okay, so val x times no, we have hailstones dot map. Well, let's do it like this. X and xv, and this is gonna be the time. So these are all the x times. And then the x time should match up with the y times, right? If our guess was good. And then we have to have a way to improve it. Then let's zip these three. So x times zip. And then how does it inform? Let's just take a look at that. Like we want all of these. We want them to all be the same. So let's look at that average of x, y, and z, I guess. That wouldn't, might that help? Let's say you just had the x's. Let's just take a look at the x's and see what happens. So delta's a guess of I let's say 400 velocity. So let's do 0, 0. And let's start at what our min bound. Move forward at 400. Yeah, so min bound. Move 400 forward at, just say 1,000. I'm inbound and then 0, 0. Hmm. And we have a bunch that are like a lot of negative times. Um, those all need to be positive times. Let's try improving on them manually. Well, actually, let's look at this. So in order to change this to become positive, we could increase V. Oh no, we could decrease the X position. Oh, let's say we start at 0. Let's see what we get. And for each of those, let's just count the negatives. Just 2 lines. Dot count less than 0. Oh, we need like underscore. Underscore 1 is less than 0. Okay, and so moving it lower when the velocity is positive increases it. Let's say, well, if we just change the velocity, make it 2,000. 186, right? The velocity is not going to change anything there. It's going to change like the magnitude of the. You could look at the average of these times. It's going to change something. So let's look at that. 0.1. Okay, if we have a higher velocity, we can get smaller time deltas. And then we want like the time deltas be like pretty similar between these three, like the same range of times. We have to do this for both like position and velocity. You know the t's by some symbol. I don't know. I have to think about this. I don't know what to do with velocity yet, so let's just count some more of these. So we had the count with 2,000. Oh no. Wait, min bound. Go like negative min bound. Min bound. And that doesn't change anything. There's like a lot of negatives. And what is hailstones that size? Like too many of them being negative. There are 300 hailstones. means a lot of these are going to be missed. And I think it's because of the velocity. So let's see what changing velocity does. Let's change this. Let's make it 10,000. Wait, changing velocity should change nothing, right? Oh, wait, we need to move to the right, actually. Make it more negative makes it worse there. Hmm. Let's try, um, let's just do inbound again. And let's do max bound. Right, it has to be at such a position. And this is if the velocity is positive. So max bound times 2. Oh, it went back down? Oh, interesting. Again, like the actual velocity doesn't matter here. Unless it's just negative or positive, right? Um, okay, let's say we have negative. Or you know what? Let's search within this peak here. Seem like something max bound times 0.5. 161. Say max bound times 0.75. 19. And that was above the max bound. Okay, so this can help us find our starting position. And I don't know how we find like lost 0.5 times max bound, which is just be min bound. Yeah. And let's look at min bound times 0.75 and various values times 0.75 times 0.5 and like a 0.25. Give me a sec. Thank you. Thank you, Icy Black Deep. Okay. So I think I do want something like this, right? Something like this, but less manual. I think so. Brett's onto the right idea with a loss function, and improving some guess. So we could like iteratively improve the guess, and this is something I can sleep on and figure out how I might do that and where like velocity might come into play. I mean, for one, like we need like all the times to be positive, and we need positions such that that will be the case. This can help us find our positions. I still don't know about velocities, but this general approach should work. So I'm gonna sleep on this and log on early tomorrow with ideas for how to do this. I think this is much smarter than trying to solve a system of equations directly. Just kind of best guess. Yeah, we'll do that. Better and better approximations. But for now, I'm going to call it a night, and I will hand all of you over. Thanks for watching my ramblings here, and all this this math attempt. I guess it's pretty when you zoom out, but that's about it. Okay, let's find someone to raid. Any of you have suggestions for who to raid? Okay, let's look for admin of code. Uptime hex 3 for Fend. Oh, I think it's Italian though. Let's just check.
E si dà anche le risposte meno male.
Yeah.
Esatto.
Let's go back. I think I saw a beginner who is on.
Max bosses too.
I mean, no, not necessarily a beginner, just starting late. So, learning Rust and Neovim. Cool. Little content warning. You're fine with that, right? They're probably okay. And it's admin code. Let's see what they're doing.
Does look cool. Free IRC client. Interesting.
Oh my god, look at those
it's a VTuber.
screenshots.
I know, right?
Oops. Much raid.
It's so radical.
Oh, that third one, the color scheme.
Very Nova.
Heckin' this.
All right.
IRC'd.
Thanks, everyone. Looking forward
gosh,
to
I love
the
that.
end of all of this.
I know, right?
Maybe we'll see y'all tomorrow. Good luck finishing yourselves.
IRC?
And thanks,
Yep.
I see
So I
Black
guess
Tea
I
for
have.
catching the
No,
mic.
not
Brett,
directly.
Sort of.
for the
Yeah.
tip about loss functions. I'll have to
Parts.
sleep on that and think about it a bit more. And everyone else for
Twitch
all the
chat is a bunch of things. And
math.
parts of it are IRC.
All right, good night.
Are Eldins a